You shall mute yourself. Otherwise, we'll feedback.
Got it. I cannot stop sharing. Okay, brilliant. Got it. Okay. Great, you muted me. Thank you. Thank you so much. Okay, one more. I would like to stay muted.
You also mute your speakers.
I should keep my video on though, Pavel? Keep my video on? Whatever. Doesn't matter.
Yeah, you could click got it. Oh, I didn't click got it.
That should do.
Okay, let me do the standard thing. Is it working? Okay, you can also use this one if you wish.
Okay.
And but then I need to plug this in order to change this.
Oh, okay. Oh.
Okay, so we are slowly plugging in, and we are almost ready to go. So, ladies and gentlemen, it's my pleasure to see you. It's been difficult 2 or 3 years, and I'm very happy finally we have a chance to meet together. Great to have you here, and we'll have a few fascinating talks coming week. Starting from Sayan. There will be a few announcements on the way. Maybe let me just say one thing. I know that we are on the downside of the wave of COVID. However, every conference where one of my students is coming back, somebody is always bringing something. Therefore, we placed in different places, especially at the entrance to the room, masks and the hand sanitizers. Please feel free to do it. I would feel very bad if you got COVID on the conference. We organized. I hope everybody will be able to get back home, without COVID and without problem with both hands. So let's hope for that. So keep in mind that there are the face masks. Please feel free to do it. And the classroom is quite big, so you can spread. About the coffee machines and other social events, we'll have a separated announcement soon. But it's good to stop talking about boring stuff. Let's speak about something interesting. So we have Sayan. When the last conference happened, Sayan was in Duke. That was good, but it's better. He's in Leipzig right now. And I'm very happy to have Sayan in Europe, and I'm even more happy to have Sayan in Będlewo opening our conference and speaking about modeling shapes and fields. Sayan, the floor is yours.
Thank you. So, turn this on. 1 second. There should be a button on the top. Ah, okay. I would like to first thank the organizers, and it's really exciting to start seeing people again live, and that's been a lot of fun. I'd say flights by Lufthansa have been less fun, but we do what we can. And I just moved to Germany 6 weeks ago. It's been an exciting and interesting process. And this is work that I've been doing with many collaborators for a while, and and it's been really fun. One of the reasons it's been really fun is that the results that we have been published in biology journals, stats journals, applied math journals, and my understanding, my very, very limited understanding of Russian is that the word for clean and pure is the same. So even we've published this in clean journals. With that, I'll start. So one of the real geniuses of Darwin was before Darwin, the way people thought about organisms and animals, and plants as well, but mainly animals, was a lineal system where people really thought about the platonic ideal of a duck or a platonic ideal of a chicken, right? Or other types of platonic ideals. And you really saw the terms that we now also see in geometry, the word generi and genus and so on and so forth. And we have a little bit of a static, but so one of the things that should I turn off the mic, Pavel?
Otherwise, we'll mess up with the sound. Try the other one.
The other one? Okay. I do. Let me turn that off. That's a good idea.
Just put it outside.
I'll just hello? Let me just go back to this one. Better now? Okay, great. Okay, so as I was saying, there's this idea that was really important, is that what you're interested in is not the platonic ideal, but variation. And this is an example from Darwin's finches. And what they realized was really interesting is that variation in the shape of the beak of the finch. And if you haven't read, it's called The Beak of the Finch. It's a beautiful, beautiful book. Okay. This is another picture. This is not my collaborator, Doug Boyer, but these are bones that he works with. These are heel bones. And one of the things he's really interested in is understanding variation in these. And one thing you could do is if you could take these heel bones, get pairwise measurements, you could build a distance matrix. From that, you can construct a tree. And you can ask, how does this phenotype tree vary from a phylogenetic tree? And this may be an indication for something that's being selected upon. So just some ideas, right? So this idea of modeling shapes, it's not new. Apparently there's a guy named Riemann who thought about it a while ago. But in more modern days, there have been kind of three primary ways of thinking about it. One was by Kendall, where he looked at what is now called the landmark-based approach. And I'll tell you a little bit more about that. Then there was a diffeomorphism-based approach popularized by Grenander, but people like Mumford also worked on this and thought about it. And lastly, there's an integral geometry approach, which I'll push harder on. Okay, and you can unify these approaches. I'll show you some pictures that slightly suggest it. Okay, so what happened back in the day, you'd go to the British National Museum and you put down landmarks on your favorite artifact, and then you put down landmarks on your other favorite artifact, and you pretend that these are all corresponding landmarks. They're the same on one and the other. And then what would you do? You'd match them. You basically find the closest match between the modular locations and scaling and translation. And this is what's called Kendall shape space. And this was a way that we modeled shapes for a long time. There's a paper, it's a little bit dark, by Pearson, where he used this approach to try to figure out whether the desiccated skull that people attributed to Cromwell was really Cromwell himself. And you don't want to know about what they did to do that stuff. Now, what they're doing more nowadays, this is my collaborator, Doug, but I also have a collaborator actually at the British Natural History Museum. And both of them have collected massive databases of micro CT scans of shapes. And they want to analyze these and they want to compare these. And it seems very sad to take this very detailed micro CT scan and turn it into a bunch of landmarks and then analyze it, right? So there's work. This was done by my collaborator Doug and one of my collaborator Ingrid, bracket 2, where they used the diffeomorphism-based approach. So you put down the landmarks, you put down little circles around them, and then you use a variational computation to move one to the other. Look at the cost of that, and that's your shape similarity. Now, it turns out in many real data sets, these are examples of fruit flies, you don't have this diffeomorphism. You may not even have a homeomorphism, right? You get extra lobes, you get extra veins, right? So these are changes. And this picture is from David Huell, and it was used by Ezra Miller in a very nice paper, I think, in the notices of the AMS. So what do the data actually look like? The raw data we get are meshes. So you get a bunch of vertices, faces, and sometimes edges, right? And so this is actually the data format. This is called an off file. So you get all the coordinates of your vertices, and then you get the triangles and so on and so forth. Okay. If you stare at this a little bit, you might say, huh, this looks like a simplicial complex. And you would be right. So simplicial complex, this is one way we think about a shape. Again, as you see, so these are not legal. Now, this is another way we think about shapes. And the reason why I'm telling you this, and there's something I want you to think about as we go through this talk. The way these data are generated, right, is through a physical mechanism. But mathematically, that physical mechanism is doing nothing but Euler calculus. So what's happening? You have a shape. It's a real object in the world. Okay, you go to a micro CT scanner. What does it do? It takes a bunch of electrons, pushes it through the shape, looks at what the projection looks like, does this from many, many, many directions, and then solves the inverse problem of reconstructing the shape. So far, so good. So now you can ask, what are the weakest conditions under which this inverse problem is well posed? And I'll tell you those conditions in about 12 slides, right? But they have to do with some notion of measurability. And specifically, they have to do with something that's called an O-minimal structure, which basically tells you just if I take any coordinate-wise projection, right? And if I look at some notion of Euler calculus on this, it's tame. It doesn't change too much, right? That's what all of this business is telling us. Okay. So we will use this idea of constructible sets. These will be our shapes in this broadest category. And we'll also talk about constructible functions. And I'll define those in a little bit, but just think about that as if I take any slice through the shape, right? My Euler calculus is tame. Okay. Now, the picture of shapes that I want you to have in your head, and this is something that Ingrid and I talk about a lot, and I think it's a really nice picture, and it actually goes through the different representations. You have a base manifold. Things like evolution, things like other things are happening on the base manifold. Think about that's where your genetics, that's what your change is happening. And then you decorate. Yeah. Oh, the mic is off. Hello? Was it back? Yeah, okay. Okay, so you have this base manifold, and things are happening. Evolution, things are happening on the base manifold. But then your objects themselves are somehow a fiber. You're decorating this base manifold with a fiber. And you can think of those different representations as your fiber. So let's say this is your organism. These are monkeys. I think they're monkeys. And then you're interested in some part of it, right? And you somehow store that as a vector. And the picture that I want you to have is that the landmark-based version, right? You have a fixed number of points. These are points in 3D. You can think of this as a vector bundle, right? Now, if I move over to the diffeomorphism-based case, you have similar thing, but you have a fiber bundle. Is how you're representing or decorating these shapes. And what we'll talk about more today is so what we'll talk about today mainly What will Hello? Oh. Hello? I do not have like with microphones. No, that's not good. I'm not sure these have batteries in them.
I mean, they were supposed to change it.
What we'll talk about a lot today is another version. And in this version, you replace that base manifold with host sets, and you will replace the fibers with stops, but we'll get to that. Okay, but the picture that I'm trying to show you is a space manifold, and then the way you're decorating the objects and representing them are different. Okay, so what the approach that I'm going to advocate for is you take a shape, somehow I transform it, and the transformation is easily representable. It's a matrix, it's a vector, it's something that I can use downstream in statistical and machine learning algorithms. I want to transform space, and I don't want to lose any information ideally. I want the map to be injected, and I want to be able to pull back. So what I mean by that is once I do some analysis in the transform space, I want to be able to come back and say what coordinates in 3 space are the most representative, right? So I want to be able to interpret what's going on. Okay, so we're going to look at 2 types of topological summaries, Euler characteristics and persistent homology. This is a picture, I just kind of like this picture. But again, it's this idea of abstracting. And so what's the Euler characteristic? Which is vertices minus edges plus faces in the mesh case. And so what we'll do is couple that with the idea of a height function. You take a direction and you sweep through the shape, you look at sublevel sets, and you ask how the Euler curve changes. So here's an example with a hand in 2D, and I'm just showing you what the sublevel sets look like. And if you take this across many directions, what do you get? If you discretize it, you get a matrix. This is capturing critical points. And sometimes we do things like we integrate it and zero mean it. So, and we'll talk a little bit about why we do these different things in different cases. I think this is homology. You have connected components, 1 cycles, 2 cycles, and then you can do persistence homology. So what we are literally doing, the analog of the Euler curve, you could do persistent homology transform, where you're just doing, Morse theory through the shape in different directions, right? And this is the 1D version for 0th homology, but you can do more, okay? Persistent diagram, it's a bunch of points in a diagonal, which says infinite multiplicity. You can define a Wasserstein metric between 2 sets of points. One of the things people have proven is that there is a stability result in terms of these bijections. So let me be a little bit more formal. So what does this Euler characteristic transform do? It takes a shape, M, which is a constructible set, looks over the sphere and maps it to a constructible function, right? Another way you can think about it, take your shape, take a direction V, go a distance T, right? Look at the sublevel set of that shape in the direction V for all values, for all distances less than T, and compute the Euler characteristic. Similarly, you can do something called the smooth Euler characteristic transform, where you take the Euler characteristic, you integrate it, zero mean it, and so this gives you L2. In some applications, these are very nice because it lets us do statistics. And lastly, you can also do what's called the persistent homology transform, where you go along the sphere, map it into a diagram, and you can do this for 0th 1 up to D-1 homology. So just checking the time. It might not be shocking that there's a commutative diagram. It turns out at a lot of applied topology talks, there are commutative diagrams. And well, probably topology talks as well. But the point that I'm trying to make is that the information that you have in the persistent homology is also in the Euler characteristic transform, and you have more information in the persistent homology transform. And I'll talk a little bit about this as we go on. So one thing we can now do is we can define distances between objects. Basically, what do you do? Take the transform, take your metric on the transform in any direction, and integrate it over all directions. So far, so good? And maybe I'll cross dimensions. Now, one thing that we will see is my computer does not want to integrate across all directions because it just doesn't like to do that. And so I have to discretize, and we'll talk about that discretization process. But at the heart of what I'm showing you, and I said this before, is actually how these shapes are constructed, and that's by the radon transform. So this is my object. You basically are pumping it through, right, with X-rays. You're looking at what the projection looks like from many directions, and then you reconstruct it. So this right here is the most general condition under which the radon transform is invertible. And this is sometimes called Schapira's inversion result. And I can talk about this, but there are a few things on this slide that are actually relevant. And the main thing is for Schapira's inversion result to work, you have to have this O minimality. That's the minimal measurement requirement. And the other thing that you have to have is kind of some notion of matching across a fiber, across projections in each direction, right? So that's kind of the important thing in this slide. And if you notice this, this is just an Euler calculus. Again, everything is happening because there is an Euler calculus. So when we first, so my colleague Kate Turner should probably be given credit of coming up with the Euler characteristic transform. Her and I worked on this, and then we worked with Doug. When Kate and I first came up with this, we improved injectivity. We almost proved it algorithmically. We didn't use a Schapira type result, and we couldn't get beyond dimension 3. And so later on, with Justin Curry, Kate and I, and at the same time, Rob and the students, use a Schapira inversion result to say that you can just do this more generally, right? Both for the Euler characteristic transform and the persistent homology transform. But this raises a question: how many directions do you take, right? And the answer in 2D is 162, and the answer is 3D is around 700, right? And these are very hard calls. No, I'm joking. But there's a question of how do I think about this problem? How do I think about how many directions there are? And if I think about this problem, does it teach me something about the math that's going on underneath? Does it teach me about the modeling, the algorithm? And does it even teach me something about the physics, right? And what I'm going to argue to you is there's something really interesting going on. Now, if you have not read this paper, read it as soon as you can. There's this paper by V.I. Arnold. It's called The Calculus of Snakes. And what does it ask you? It asks you, if I tell you what the critical points of a function are, can you tell me how many homologically different functions are there with these critical points? What is amazing, and V.I. Arnold is amazing, he gives a closed form solution. He gives a closed form solution using Coxeter groups and other ideas, and it's absolutely amazing. Okay, so now in our case, I'm going to tell you the following. I have some moduli space of shapes embedded in D dimensions, okay? And they're going to have a few properties. At each vertex K, I can lower bound some notion of curvature. Now, why do I need to do that? It turns out if you have something that's super flat and you have another thing that's super flat, it's really hard to tell them apart, right? So if you want to tell apart shapes, you need some control of how flat you want to be, right? There are questions about, like, I think it's a joke. Can you tell apart Lubbock, Texas from a pen? Right? If anyone's been to Lubbock, it might be. So there you have to have some bound and flatness. And the other thing that you have to have control over, once you have that bound and flatness, if you look in the cone related to that curvature in any direction, right? The change in critical points can't be crazy. You have to have some control of the changes, right? So that these are the two things that you need. And if you have those, I can give you a bound. But before I give you a bound, I want to show you a picture. And I want you to actually think about the radon transform. So what's happening is we are taking a sphere, right? And we're chopping up caps of it, right? So you're stratifying a sphere and you're chopping up caps. And what you can say is if you have some notion of regularity, which I just defined on the previous slide, if I know what the Euler characteristic looks like, let's say around that orange dot, and then I just change it slightly, there's a linear relation between these Euler characteristics. So what we're saying is, once you look at these projections, things are locally linear across these angles. So, one thing I could have told you is, hey, when you're doing your data analysis, don't even bother inverting the, and coming back, right? The transform, right? Well, we write, you got all these projections initially, and then we reconstructed the shape. And then what we're really doing, in a sense, is just undoing that, and then analyzing the data. And again, the reason why is once you look in the projected space, things are locally linear. And so this is our upper bound. It's ridiculous, but it's an upper bound. Now, there's a practical problem hiding behind this, which we started working on, which is, I'll give you an example. We are doing a project right now where we're looking at gliomas, and we're doing imaging, and we're observing people with gliomas. And the idea is, unless things get really bad, we're not going to treat them. The idea is not to treat them, because sometimes the treating the malignant cancers can evolutionary put pressure on them, so they become worse. Right now, let's say you have a radiation budget, right, and that you can't radiate a person all that much, so you want some constraint on the imaging. So a very basic question is, if I have a priori, or this could happen in breast cancer, if I have a priori set of data, can you tell me how many directions and what direction I should use to get an epsilon approximation of the micro-CT, right? This raises that question. That's a practical and really useful question. Okay. Now, I told you before, there's a notion of shape space when I talk about landmarks. There's a notion of shape space when I talk about diffeomorphisms. So you can ask me, is there a notion of shape space when I talk about these Euler calculi, like the persistent homology transform or the Euler characteristic transform? And the answer up to a month ago was we don't have, but now we do. So this is work with Justin and a really wonderful student, Shreya. And so the first thing we did was, you can take this fiber perspective and use it to define a sheaf perspective on the persistent homology transform. So you can take the persistent homology transform and quote unquote sheafify it, right? And that's what I'm telling you right here. It's a push forward of a constant sheaf. And so this is what the persistent homology transform looks like. And this is the analog of the fiber in the case of the diffeomorphism-based approach. And so then what do you do? Okay, the objects are constructible sets. You replace the notion of the base manifold with posets and inclusions, right? That's what replacing that. But you need some notion of continuity, right? And what you do is you do some work, realize that this is a Grothendieck site, and that there is a form of a homotopic limit here, and you have a sheaf. So we have the sheaf theoretic construction. And one of the things that was interesting that came out of the sheaf theoretic construction is, if I have a mesh, all I need is 0 degree homology. You actually don't need higher order homology to capture the information. As soon as you have positive curvature, you do. So the sphere, you do, but you can always triangulate, right? So again, this is one of the things we learned, which was kind of cool. Okay. I told you we did some work that was applied. If anyone thinks that most of what I talked about so far was applied, they're delusional. So now let's talk about the applied stuff. Okay. So this is an example of this is a glioblastoma. Okay, it's a brain tumor, and you can use some code to segment it. And I'll tell you that is not easy to do, but there's stuff that works. And so what we're going to try to do here is the following. I have 92 patients, and I have matched gene expression and MRI data. Okay. And these morphometric features are features that a reasonably large group of oncologists and radiologists work together to figure out, we think these are good. These are kind of pointless, or like how round is it, how wide is it, you know, what 5 feature. And these are what we did from our representation. And we wanted to ask 2 really simple questions. How accurately can you predict disease-free survival? And how accurately can you predict overall survival? Okay. So, and one of the questions you might want to ask is, which of these features are doing better? Okay. Now, there's a basic thing that's going on here, which is there's this area of radiogenomics, which is including imaging radiology data with genomic data. And a lot of the motivation for this is how do we get more regular information from patients in a non-invasive way? Okay. Another way you can think about this problem is, how do I use shapes in a regression model? Okay. So this is how we did it. You can do it in other ways. We took these slices of these MRIs, took the Euler characteristic in different directions, and we just stacked that up as one massive vector. Now, we could have done it in other ways. And there's one thing that I think is really, really important when we think about applied topology, which is picking your filtration, right? And I think we always go, oh, I did this filtration, I did that filtration. But it's really worth it to think about the filtration and what you want to represent. What do you want to mod out, right? So there are cases where, you know, you are rotationally symmetric, right? And so you might want to mod that out. So again, I think it's really, really important to think about that filtration. Okay. We used initially the following model. Later on, we've also used deep neural networks because everyone else does. But we used a very simple model. It's called the Gaussian process model. And this is, again, where choices, you think about choices, you actually matter. I didn't show you results, but when we studied how similar the bones are of those calcanea of the different really monkeys and lemurs, we use the persistent homology transform because it's a little bit more stable and it worked a little bit better. Here we used the smooth Euler characteristic transform, and for 2 reasons. Functions in L2 have a nice inner product structure, right? Whereas persistent homology, you try to define a covariance kernel or covariance matrix based upon inner products, it's probably not going to be positive sum depth, right? So there's that issue. And in statistics, there's a tremendous literature on something called functional data analysis, which is how do you take curves and do stuff with them, right? And what I've told you is I've taken the problem of modeling a shape and turned it into a collection of curves in L2. And so I can just apply functional data analysis. And this notion of Gaussian processes is a very classic idea of that. So just in 2D, these are my data points. I put a little Gaussian bump on each one of them, right? I weight them, and this is the notion of my regression function. And what's great is everything is linear algebra and involves one annoying matrix inversion, that's n cubed, but other than that, it's not so bad. Now, I can ask you, should I use just a linear correlation as my similarity between the points? So that's called a linear kernel. And then I can also look at distance-based kernels. One is this notion of a Gaussian. Another one has heavier tails, it's called Cauchy. And then what we can do is we can look at all of these and ask, okay, which method is doing the best? Which of these features are doing the best in classification? And we find down here are the topological features. So what do? We take 80% of our data, build a model, test on the accuracy on the remaining 20%. We'll do it a bunch of times. And this is giving us the root mean squared error. And this is telling us what percent of time these set of features are doing the best, right? So you're actually seeing this representation is useful. It's actually doing something, right? So that was kind of cool. So then we asked the question, That's all well and good. And, classical statistics, the thing that you do right after you do regression, people do variable selection. They ask, which of the coordinates are the most relevant, right? So you can actually ask the same exact question for a shape. It's a little bit harder because we don't really have coordinates. But you can ask what points in 3D space are the most different between the shapes? What have the greatest amount of variation? And so that's what we did. And we came up with a method which my collaborator Lauren is much more creative and much more cool than I am. So he called it Sinatra. So I'm going to first give you a picture, right, of how Sinatra works. Let's say this is class 1, class 2. You can think of these as the molars of lemurs that eat insects, the molars of lemurs that eat fruit. Okay? So then what do? I basically compute the Euler characteristic transform. So here we don't use the smooth version. I'll tell you why in a second. But actually, I'll just tell you why right now. If you smooth this, you're averaging information across all of the points, and you don't want to do that, right? Because if you want to do variable selection, ideally, you'd like to see where are those chunks, right? Where are the differences? Okay? Okay. So then, and I'll tell you what our variable selection algorithm is in a second, but what we do is we use a variable selection algorithm to tell you in which direction and at what height, right, do I have the greatest amount of variation. Okay. So once I have that, then transforming that back to a 3D coordinate is a problem in projective geometry. It turns out, in this applied case, is not so bad. And so what I'm showing you here are false color pictures, where the red are the locations that are most varied, and this is between one class, and this is between another class. We did, the paper we wrote, we did not have biomedical applications, but when we put our paper up on bioRxiv about 6 days later, we got an email from people at Genentech where they were using this for case control studies in psychoactive drugs. That's when we realized we should probably put some type of license on it. But anyways, okay, so, oh shoot. I screwed up. Give me 1 second because I realized I just deleted a bunch of slides. This should have some of them. Sorry about that. I thought I kept them. Oh, shoot. Okay, today we are having some difficulties. Something will work. Okay. That's why I picked the wrong one. I'm really, really sorry. I do have one that I know works. I know. I'm yeah. Nothing horrible should happen. Did it pop up? Oh, no. You stop share. Okay. Okay, great. So this should work. Okay, great. Yeah. And again, I really apologize for this. Okay, great. Okay, so I told you about the classification algorithm we used, right? That was the Gaussian process. Okay, so we worked out a way of thinking about variable selection for nonlinear regression. So in regression, what do you have? You have a bunch of coordinates and you have effect size, like this beta, which tells you somewhat how relevant that is. It's no shape of an effect size, right? And so we generalize that for a nonlinear case, where you fit a nonlinear function, let's call it f, you project back onto your coordinates, and that gives you an effective notion of beta. Now, the other thing that we were able to do is we had this as a sampling algorithm, as a Bayesian algorithm. So we had Monte Carlo draws of these beta hats. So you can actually think of getting all of these estimates of the beta. And then we're going to make a really, really reductionist assumption and pretend that this is multivariate normal, just to make our lives really easy. And the reason we do that is in the following step. So one way of thinking about whether a player is useful or a variable is useful is you just remove them from the team, and you see how often they win, right? And this is what we call centrality in ranking, right? If you remove one player, the team might lose a lot more than if you remove another player, right? And so what you can do, and this is why we pretended everything was multivariate normal, is you can just remove the variable, look at what the Gaussian distribution looks like, or you can integrate out that variable, look at what the Gaussian distribution looks like, right? These are the same dimension, they're Gaussians. You can compute the KL divergence closed form, and this gives you a score. Okay, and again, the score is 0 if and only if there's no information. You normalize that score, and that's what we call the rate variable. And that rate variable is what we're using to do the selection. That tells you which direction and in what height the most variable points are. Okay, so that's an evidence of association. Okay, now I can go back. Stop and share. And another point I want to make is, there we go. I really do want you to think about this as a pipeline with submodular. You could have swapped out the Gaussian process with a neural network. You could have swapped out one of the representations possibly with another representation if it works better, right? And so the last part is, once I give you the direction or the height, how do I recover the 3D coordinate, right? And the way we recover that is actually goes back to that picture which I was showing you with the caps. So if I know in one direction, right, I know direction V is important, and I know height, let's call it T, is important. What I can do is I can just generate a small cone right around that to recover the 3D direction, right? So this is exactly what the algorithm is. And so you can also think about this in terms of linear algebra, right? You don't know X, Y, Z, right? This is the direction, these are the heights. You construct an over-represented set and try to recover X, Y, Z in a small cone. But the actual algorithm we use is just this. You take the little cone, you look at the intersection set, and that's what you call your relevant coordinates. Okay. So one of the things that was really interesting for us is we have an algorithm, we think it works. We've done simulations on really silly things like little spheres with spikes on it. But how do we know that this actually works in a more controlled simulated case, right? How do we think about this? And so what was really fun is we went into the computational geometry literature, and there are people who make characters, right? So you can take a tooth, or you can take a face, and you can make the nose bigger, or you can make a cuspid larger, right? So that's actually what we did. We took an original shape. We actually controlled the way that we caricatured it, and then we looked at our reconstruction, and we saw, were we recovering the right features? And these are not so exciting. These are a bunch of ROC curves on more or less complicated settings. But the point was we understood a little bit. And so our last example was on these are all lemurs. And this one is known to have this type of cuspid. As you go further away evolutionarily, it kind of starts going away, right? And so we said, if we construct a classification task between this one and this one, this one and this one, and this one and this one, and then do the sub shape selection. What does it look like? Does it give us back something we would expect? And again, we started seeing that in this case, we weren't really seeing the cuspid so strongly. You start seeing it as you go a little bit further evolutionarily, and even further you start seeing it. So you start to recover some of the things that you would actually want. Recently, and this was really mainly my collaborator Lauren's work, and I came along for the ride, is we adapted this to protein structure. So here you have the 3D coordinates of the protein. Then you thicken it out, put right in the right molecules. This is what's called a ribbon diagram. It's another way of representing it. And we basically applied something very similar. You have these two types of, maybe a wild type protein, a mutant protein. You then go back and you go from here, construct a simplicial complex. You look at topological features. And then here we used a slightly different algorithm because in the case of the protein, you don't get so smooth jumps. Sometimes the jumps are more localized. We did variable selection and again, did some type of reconstruction. And from that, you can get these types of ribbon diagrams. I just wanted to show you one case. We found something called the gamma loop of this lactamase, and it's induced by this mutation, right? So again, this is a way you can start manipulating and getting at what might be underlying differences between shapes. And again, it's a common pipeline, but you have to think about what's the right representation, both in terms of the shapes, but as well as in terms of the algorithms. So recently, we've been asking, okay, that's great, we can do this with shapes. What about for soft tissues, right, where it's not just a shape and it's a vector field? So the answer there is, how do I do Euler calculus on real functions, right? And there are people who've worked on this. There's some very nice work by Ghrist and Baryshnikov and their colleagues, and they give a form of this with rounding. But what we did was something a little bit simpler. We worked on something called the Lifted Euler Characteristic Transform, where you filter not over a direction only, but also the actual value. Now, one of the people who use this notion of a height function a lot for MRI, but also for cosmic radiation, were people like Jonathan Taylor and Robert Adler and Keith Worsley. And what they were really interested in are the topological structure of random fields, right? And so they're filtering by what the actual function value is. We're doing the same thing, but we're also filtering in directions. So this gives us a bigger matrix, right? If you just concatenate everything. A lot of the things that I told you about the Euler characteristic transform over to the lifted Euler characteristic transform, and we can get bounds on the number of directions. But what was kind of fun is we applied this to a breast cancer data set. And we effectively did as well as an extremely well-trained neural network, almost off the shelf, using a simple Gaussian process, right? So that was kind of cool. Okay, we will end in time. There's so much to do here, right? There are ideas of dictionary learning here. I didn't talk about this, but another really good thing about this perspective of having a base manifold is if you actually want to do more formal phylogenetics. So if I want to say that these collection of molar teeth, right, from Madagascar, which is where the molars are evolving just Brownian motion or Ornstein-Uhlenbeck, or what's called the burst model. What you can do is you can define a Gaussian process on the base manifold using very classic genetics ideas, define a fiber on the bundle, and try to integrate it out and get more formal estimates of the selective pressure. Now, when you do this, there's one really important thing that I didn't put this slide up, is the following is a fact. If you want to put a stochastic process on a manifold, and if you want to define a kernel function, which gives you a covariance matrix that's positive, definite, your first inclination is to do the following, which is principle. Write out that covariance function that's e to the minus and GOT system. Okay? This seems Not a crazy thing to do. You can prove that that will not give you a positive definite matrix unless the manifold you're looking on is isometric to Euclidean space. And if it is, this is just a pointless exercise, right? So the way to quote unquote correctly do it is you have to solve an SPD. But anyways, there's a lot of interesting work there. Integrating the genomics with imaging. One of the things that we really want to do is generate random shapes, right? How do I turn this into a generative process? There's absolutely beautiful work on lifting stochastic processes onto manifolds using fibers. And this is work Galvin, Eels, Ellsworthy. There's a wonderful book by Elton Su. And there's a really basic question, which is extremely open, is how do I extend this to sheaves, right? How do I extend this to situations where, you know, the dimensions aren't all the same, right? And then how do I do this? There are, you know, practical problems in extending this to structural biology and microscopy. And one of the things we're really trying to do now is, so you have this diffeomorphism approach. I gave you, or I suggested that maybe you should use this Euler calculus-based approach. Can I show you under some metric, under certain things that's reasonable, that when I have this Euler calculus-based approach and I have diffeomorphisms, I get back to the fiber case, right? These things kind of match up, you know, for the limited case where they're the same. This also begs a very basic question. When you don't have diffeomorphism, what is a gold standard distance between two shapes, right? Like, do you use Gromov-Hausdorff? Hopefully not, I don't know, right? There's some work where, you know, that was done using Hadwiger integrals to compare these, right? But that's still quite open. Integrating with the physics of imaging, I think there's a lot of interesting things there. Over time, there are people who've talked to me. Turns out that now there are people in multiple countries that have given me money. I thank all of them. I thank you. And again, the main thing I want to tell you is that this has been a really fun project. And, you know, we've worked with all kinds of people using all kinds of tools. And hopefully it continues. And I'll end with that.
Much questions.
Yes, Dimitri.
Well, the first is a trivial question. What is number 3?
That's me late at night forgetting.
That's okay. So my real question is this. You started by talking about landmarks and alignment. Then when you went to these transforms, you never came back to the question of like, how do you factor out this O3, right? Because you get
That's
projections and then what?
So Dimitri's question is really good. So let me. So when we submitted the Sinatra paper, we sold it as, you know, you can do all this stuff without requiring landmarks. And one of the reviewers very naturally asked this question: how did you register them in the first place? Okay. So two things. The way, I'll tell you one approach of registering, because I worked on this problem, which is first compute all the pairwise distances using whatever you can. Then you kind of rotate them to align them the best you can, construct a minimum spanning tree, then iterate this whole process until things don't change. Okay? Now, what I didn't show you is a slide we have, which is if you take, let's say you have a curve. You think of your directions as random, right? And then you just think of this as a collection of a bunch of random vectors. And you basically look at optimal transport between these two. They'll match. So what you can do is you can use that idea with an encoded rotation matrix to try to do the alignment. Very much like ICP, yeah.
Good. Other questions? Okay. Yeah.
So in the part that you were talking about this kernel function on the Riemannian manifold, so the assumption is that the data set is on the Riemannian manifold, and you said that if you just take the geodesic distance on this one and just take the exponential of minus of this distance, you just have the isometry with Euclidean space.
So
And then why this happens? Because this Euclidean heat kernel is some kind of discretization of the Riemannian heat kernel. Why should we have the isometries instead of just
Right.
discretization?
okay, what I was trying to say is the only case where when you do this and that kernel is positive definite, right, is when the other underlying space is basically Euclidean. It's isometric to the Euclidean space. Now it could be that the negative eigenvalues are small, and so you could truncate them and you can go on with one, right? But what the real point is, if you work out when is lifting Brownian motion on a manifold mean, when does it work, right? The basic construction is you have random curves on your base manifold, you lift them, right? And then you show you have some type of martingale, some nice structure on that lifted structure. And then you take that and you embed it, using Nash or something else, right? And you show that you have a martingale, a nice structure in that space as well, okay? And then you show you can walk back and forth between all of these. Now, the natural way of walking back and forth between all of these is actually solving a stochastic differential equation, right? So that's why you go back to something where you have the Laplacian times your function is equal to Brownian motion. And you solve that, and the solution of that gives you your kernel, right? Because it goes back to this Brownian motion, SD, right? You might get lucky, right? And you might be very close to positive definite. And if you just truncate, meaning things far enough away, you just set to 0, you might be okay. But no guarantees.
Just a short question. When you use the minimal structures for describing your shapes, what kind of a minimal structure do you use?
Okay, so the short answer to that is we never we never specified, we just use the fact that for the minimal structure, you have tameness, so you get something back. But really what we're using are semi-algebraic sets.
Okay,
Right.
this was my idea that you
Yeah.
just semi-algebraic.
Yeah, exactly.
Mhm.
We just didn't want to specify all of that.
Because that if you go to Parthian or some exponential or minimal structure, then this kind of estimates that you write in terms of complexity are somehow doubtful.
Yeah, they're shady.
In non-polynomially bounded.
That's right. They become shady, exactly. But yeah.
Good, any further questions to Sayan? Not, let's thank the speaker again. Just quickly change the speakers.